Welcome. In this series, we are exploring a fascinating intersection of geometry and quantum mechanics, the fractal uncertainty principle. To understand where we're going, let's briefly recall where we start. In classical Fourier analysis, we are bound by the Heisenberg uncertainty principle. Intuitively, it tells us that a function cannot be highly localized in physical space, here on the left, and Fourier space, on the right, simultaneously. As we squeeze the wave in position, it inevitably spreads out in frequency. The more precise we are here, the more uncertain we become there. But recent developments in mathematics ask a more subtle question. What if, instead of simple intervals, we restrict our function to live on fractal sets, specifically, sets that are porous containing holes, at every single scale? These are sets like the Cantor set, which have no solid intervals, yet contain infinitely many points. The fractal uncertainty principle states that the classical restriction still holds, even in this porous environment. You cannot trap a quantum particle inside a fractal set in physical space if its momentum is also trapped in a fractal set in Fourier space. Mathematically, this manifests as a loss of energy. If a function's frequency is confined to this fractal y, then the amount of energy it can keep on this fractal x must decay. That decay depends on the scale h and the fractal dimension beta. This principle is the key to controlling high-frequency waves in complex geometric settings, as we are about to discover. Before we dive into Alex Cohen's higher-dimensional discoveries, we must establish the foundation. The 1D fractal uncertainty principle proved by Bourgain and Dyatlov. Theorem 1. 2 quantifies a fundamental limit on localization. It states that a function cannot be highly concentrated in both a porous physical set and a porous frequency set simultaneously. Let's break down the geometry behind this inequality. First, consider the physical space, x. X is a subset of the unit interval, but it's not the whole interval. It is porous down to a small scale, h. Think of it like a Cantor set a structure with holes at every scale from 1 down to h. Now, look at the frequency space, y. This set is much larger, extending from negative h inverse to positive h inverse. However, it is also porous. Here, the holes appear at scale 1, relative to the massive size of the domain. The Bourgain-Dyatlov theorem tells us that if your frequencies live in y, then the energy of your function restricted to x must be small. Specifically, it decays by a factor of h to the power of beta. This polynomial decay is the signature of the fractal uncertainty principle. This 1D result is the bedrock. Now, let's see how Cohen generalizes this to higher dimensions. Building on our introduction, we need to define exactly what we mean by a porous fractal set in higher dimensions. First, let's look at the standard definition, porosity on balls. Imagine this square is our space and we test it with a ball B. For a set to be porous on balls, every such ball must contain a hole a smaller region where our fractal set is completely absent. Now, consider a much stricter condition required for our main theorem, porosity on lines. Here, we test the space with a straight line segment. To satisfy this, every line segment must contain a hole centered directly on it. The set cannot contain any full line segments. Why the distinction? In 2 or more dimensions, a simple line like a thin wire is porous on balls because it's surrounded by empty space, but it fails porosity on lines because it is a line. Thus, avoiding lines is a much stronger structural condition than just avoiding balls. To understand why we need this stronger porosity on lines condition, let's look at a critical counterexample in 2 dimensions. Consider our set X to be a simple, infinite straight line. First, let's see if this set satisfies porosity on balls. If we draw a ball anywhere centered on this line, does it contain a whole region of empty space not touching the set? Yes, it does. Because the line is one-dimensional and the ball is two-dimensional, there is always plenty of empty space inside the ball on either side of the line. So this set is porous on balls. Now, let's test for porosity on lines. Does every line segment passing through our set contain a hole? Let's look at a segment, tau, that lies perfectly coincident with our line x. If we scan along this segment, do we find any gaps? Do we find any point that is not part of the set x? No, the line is continuous. The segment is entirely filled by the set. There are no holes. This demonstrates that porosity on balls is too weak for higher dimensions. It allows sets like this line, which are too solid to satisfy the uncertainty principle. We need the stronger porosity on lines condition to rule them out. Now, we can formally state the main result of the paper, Theorem 1. 1. It combines the geometric concepts we've just built into a precise inequality. Let's break it down. First, consider a set X in the physical unit cube. We assume X is porous on balls, the standard notion of porosity across scales, from H down to 1. Now, we turn to frequency space. Consider a set Y in a much larger box, scaling up to H inverse. Here is the crucial difference. Y must be porous on lines. Notice the asymmetry. In higher dimensions, avoiding balls isn't enough for the frequency set. To get an uncertainty principle, the frequency support must avoid entire lines. If these conditions are met, we get the fractal uncertainty principle. If a function's Fourier transform lives in Y, then its energy on the physical set, X, is suppressed by a factor of H to the beta. This tells us that a function cannot be simultaneously localized to a porous set in space and a line porous set in frequency. Proving this result requires a powerful new tool, a higher dimensional version of the Bueling-Malliavin multiplier theorem, which we will explore later.